Okay, so today will be chapter 4, yeah. So chapter 4 is about the sequential circuit design. Before this, we have learned combinational circuit where uh, where the output of the circuit, combinational circuit in chapter 3, the output is depend on the input. All right, it will change immediately when the input change. All right, now we will look at another digital circuit. We call it sequential circuit. So this sequential circuit is very important in digital electronic. All right, the characteristic of sequential circuit is that the output of this circuit not only depend on the uh, present input, the input, but also depend on the previous output value or the memory of the circuit. We call that state, state, right? So, for example, we are in state A, the next one will be state B, or the next one will remain as state A, all right? So the output of the sequential circuit is also called a state of the sequential circuit, right? So what we will learn is latch and flip-flops. Actually, you learned this already in digital electronic class. Okay, so this is a revision and register. All right, but we will look at in detail how to design in Verilog also. We will learn a shift register. All right, another kind of register also. Okay, where we can shift the data to the right, to the left. And another application of the register is the counter. Okay, we will where we can count the number. All right, count up 0, 1, 2, 3, or count down. All right, or you count in step 2, 4, 6. You can use the counter. It is very important also in digital electronics. And last but not least is the finite state machine, or what we call the FSM. So this is the core of this course also, because after this we will use this finite state machine a lot in the design in chapter 5 and chapter 6. Yeah, and we will look at what we call the ASM, or algorithmic state machine. So this is actually the method to design the finite state machine. Okay, so this is what I have said before, where the combinational circuit are the circuit that the value of each output depends solely on the value of input applied to the signal applied to the inputs. All right, so remember, combinational circuit, the output is depend on the uh, input. All right, so it will change immediately after the input change, one of the input change. All right, but for the uh, sequential circuit, the output not only depend on the present value of the input, but also the past behavior of the circuit. All right, past behavior or the past output, the output of the circuit. All right, or we can say that the memory of the circuit. Yeah, okay, that we call the sequential circuit. All right, so this is how we create the memory in digital electronic. So the first thing is the latch. The latch. So this is what we call SR latch. SR latch. All right. So this is basic latch. All right. So we create the memory by having this signal. The output is feedback to the input. This will create memory to your circuit. All right. So this is the SR latch, where S or we call set and reset latch. So this is the characteristic of the truth table. So this latch, when the value of the S and R are 0, 0, so the output will not change. Not change means that memory. This represent memory. If the input is 0, 0, so if Q, the previous Q is equal to 0, so it will remain 0. But if previous Q is 1, the previous value of the output is 1, so if nothing happened at S and R, so it will remain 1. So this is memory that we talk about. All right. But if R equal to 1, S equal to 0, so QB is uh, equal to 1. All right. And we, if S equal to 1 here and R equal to 0, so this one is QA is 1, QB is 0, and when both are 1 1, so both output will be 0 0, right? So and this is the timing diagram of the uh, SR latch. So you can see this arrow is actually means that this S will affect this output first. As when we look at the uh, schematic here, we can see that QB is the output of S, output of S. That's why QB will actually will change first. When S changes, QB will change to from 1 to 0, and after that followed by QA. All right, because QA is actually from this QB first. All right, so when you see the timing simulation in the Quartus, you can see that this will happen first before this. All right, but when we look at functional simulation, uh, we see that this is looks like happen at the same time, but actually this one first uh, in first and has some small delay between this and this. This happened first and then followed by this one. But for if this one, if R change, so this will change QA first. So you can see that because R is QA is the output from this gate and the input is R, so this will affect QA first before QB. So we can see that the arrow is like this. Yeah, and how this go to 0 and 1 is according to this truth table. You can go back and look for yourself how this is generated. All right. So quite simple. So you know this already in the last previous course. So this is uh, an improved SR latch, or we call it gated SR latch, where we have clock, all right, that feed to the SR latch here. Okay, so it depends on the clock. So in this case, if there is no clock, all right, if there is no clock, or clock is not active, in this case is 0, so the output of the Q is not changed. So again, this is memory, right? If there is no clock, but if there is a clock, all right, if the clock is active, so the output at Q will follow this is the same as this one. All right, so this is the timing diagram, and this is the symbol of this gated SR latch. So pretty easy from here. And now come to the another type of latch, which is the D latch. So D latch is actually more useful in practical, in practice, uh, than SR latch. So in computer, the register, right, that is used to store data in your computer is actually made of the D latch. So from this, from now, we will use D latch instead of SR latch in our design. All right, so from now we will use D Latch in designing our register, in design a bigger circuit in chapter 5 and chapter 6. Everything will be D Latch, uh, D type. All right, so D is actually data, okay, where you have this data and you send this data to the output. All right, so when we look at the characteristic, so we will see that if there is no clock, all right, so D uh, D either 0 or 1, we don't care, but the output will be the same, remain the previous value. All right, so when there is no clock, uh, the output at Q will remain the same, from the previous value. But if the clock is active, so if D equal to 0, the output will be equal to 0. When D equal to 1, the output will be equal to 1. All right. But after the clock, for example, when we look at this, all right. So this is our clock. Uh, D going to go to 1 here, but there is no clock. So Q still remains 0 until we have clock here. All right. We have clock here. Now, Q output is go to 1 because here D still 1, until here D go down to 0, but because there is no clock at this point, so it remain 1 until the next clock active here. All right, clock active, then because D is 0 here, so it will go down to 0. All right, and this cycle will repeat, here go up because we have clock, and here is 1, D is 1. All right, so this is the characteristic of the D latch, and we have the graphical symbol of the latch is like this. You have box, you have D, this is the output, and this is the output bar, or Q bar, and you have clock, right? And come to the next one, which what we call the D flip-flops, and this is the most important one. All right, we will use D flip-flops later on. All right, so what is D flip-flop and what is different between flip-flop and the latch? So the flip-flops is sensitive to the clock edge, rather than sensitive to the clock level. So for example, latch. All right. So we will see here, whenever clock is active, all right, means that you need to follow the input. So you will see here, when input going down here, Q also go down, all right, immediately, all right, because here in this area the clock is active. But for flip-flops, all right, we see that when the output QS, all right, the output here QS, okay, is follow D when the clock, or at the clock edge. So in this case is negative edge triggered, you have bubble. So from here you don't have this symbol, also the triangle here means that this D is actually the flip-flop, but if you don't have that, this is actually the latch. So flip-flop means that the output is clock triggered, clock edge triggered. So for example, in this case, we can see here, right? We can see here, if we look at the level of the clock, here the if we look at the latch behavior characteristic, so QS should go up already because because D is going up here, right? But because this one is edge triggered, means that we only look at the edge here, all right, negative edge. So this one is positive edge, no, not look at D yet, but here you see, all right, negative edge, and because at that edge is positive, right, so you need to not positive, sorry, D is equal to 1, so you QS will go to 1, and it's remain 1 until the next clock, right, negative clock edge, which is here. All right, here the clock is active already for the latch, but the flip-flop we will look at this edge only. All right, that's why the signal is not going down here. All right, follow the D. All right, although the D is going down already, but Q still remain the same until the negative edge here, and we will go down. All right, so this is the characteristic of the D flip-flops, and to build a D flip-flop, actually you use two D latch, connect like this, and the first one is, we call it the master, and the second one we call the slave, and we connect the clock with this inverter, and we get the D flip-flops, right? Negative edge triggered, okay. Now come to the important part, how to create the memory in Verilog, right? So this is how we write using the behavioral modeling. Okay, when we write, always control, we have two input here, control and B. If control A equal to B, done. So if we look at this code, when we learn last time in previous chapter, when we learn combinational logic, all right, I told you that you don't write something like this when you want to design a combinational logic, right? Because if you have if, okay, if this signal equal to 1, yes, A equal to B. What about else? Else. What if the control equal to 0? All right. What happened to A? Okay. So if you write like this, the Verilog will uh, automatically do this for you actually. All right. So let's look at this. Okay, when you write something like this in Verilog, always uh, control B, right? If control A equal to B, okay, when you compile this Verilog code, what Verilog could do for you is actually like this. It will give you this statement, all right? So this represent memory, because we will see that if control equal to 1, yes, A equal to B. But if control equal to 0, A remain the previous value, A remain A, all right? When we say that A remain A, means that the output remain the same whenever the control signal is equal to 0. This is memory, okay? So if you want to design a combinational logic, don't write anything like this, because it will create memory for you. You will not get combinational logic, but you will get the sequential logic, the latch instead. So this is a latch actually. Now, how to create the D latch? All right. So this is the code to create the D latch. All right. The name here, you have D input, you have clock, and you have Q output. The input is D 1 bit, also the clock 1 bit, and output is Q. All right. And you need to declare Q as right, because why? Because Q is a variable. Q is a variable inside the always block. All right, and you assign a value to this variable. You assign D to this variable. So this variable must be declared as right. Okay. So if you do this, if clock active, so Q equal to D. All right, or you assign D to Q. And what about else? You don't have else. Actually, you have else Q equal to Q here. But in Verilog, no need to write that. All right. So this will give you D latch. But how to create the D flip-flops, the edge triggered flip-flops? Okay, so this is how we do. The signal is the same. We have D, we have clock, and we have rec Q, also the same. The difference is in the sensitivity list. This is the difference. All right. So if we have this, like this, we don't have edge triggered clock. So your signal, the input clock and your input will be inside the sensitivity list. But if you want to create the edge triggered flip flop, you need to write this post edge. This is positive edge triggered flip flop and clock. All right, Q equal to D. This will give you the flip flop, positive triggered edge, positive edge triggered D flip flops. Now come to uh, the uh, the the method of describing the memory element or the flip flops in Verilog. So actually we have what we call the blocking and non-blocking assignment. So what is assignment? Assignment is simply a simple equal symbol. So when we write in Verilog, when we say A equal to B, this is assignment. Okay, so this is assignment. So that's why sometimes I said B is assigned to A. All right, assignment. Okay, so there are two assignment type in Verilog. The first one we call it blocking assignment. Blocking assignment. And the first one is blocking assignment, and the second one is the non-blocking assignment. So the non-blocking assignment, the symbol is this. This is B assigned to A also, but this is called non-blocking assignment. Right? Non-blocking assignment. What is the difference between the two? The difference is the function is the same, assign B to A, assign B to A, but the difference is when the Verilog compiler, all right, synthesize the code, it will give you different kind of circuit based on how you write the code. All right, so let's look at the example. So before this, when we design the combinational circuit, we use blocking assignment, right? We use all this symbol, the equal symbol, right? We use this bit. all of our assignment before this, we use the blocking assignment. So blocking assignment and non-blocking assignment is the assignment inside the always block, actually. So when we have always block, like this, right? And we write something like this. So, okay, so this is using a blocking assignment. So the Verilog compiler will evaluate the output in sequence, one by one. So it will use the previous G here to evaluate the new F. So it will evaluate line by line, means that the output from here will be used in this input. All right, that is for blocking assignment. But for non-blocking assignment, all right, it will evaluate separately, separately. All right, just like we use concurrent assignment in uh, um, in data flow modeling. All right, so to understand this, let's look at the example. So for example, when we design the flip-flops using blocking assignment, all right, so this is the flip-flop that we want to design, for example. So we have two flip-flops and we want to connect in like this. The structure is like this, cascade. So the output of the first flip-flop Q1 is connected to the input of the second flip-flop. Yeah, all right, and using the same clock. So we actually can or we'll write the code like this, right? So example, module example. So we have D, we have clock, we have Q1 and Q2. All right, D input, clock also input, rec Q1, Q2. So always gain post H because we have post H clock, post H. And begin, we write Q1 or D is assigned to Q1 or Q1 equal to D, and Q2 is equal to Q1 or Q1 is assigned to Q2 here. All right. So it should look correct, right? It's look correct. But what the Verilog compiler give you is that after synthesize is that something like this. All right, because it will conclude that Q2 is actually equal to D as well, right? Because Q1 is equal to D and Q2 is equal to Q1, means that Q2 is equal to D. So it will give you something like this. You have flip-flop and Q2 is equal to D and Q1 also equal to D. All right. So it's different. This and this definitely will give you different output. All right. Or sometimes if you don't have Q1 as output like this, right? For example, you don't have Q1 as output like this, you may get something like this. Because we say that Q1 is equal to D and Q2 is equal to Q1. Okay, so what the Verilog will do is that Q2 equal to D, same thing. Okay, so it will give you one flip-flop. This is sorry, this is D and this is Q2. because it will see that the Q1 is redundant, because the Verilog will understand that Q2 is equal to D. All right, so it will give you only one flip-flop, Q2 and D. All right, because it will see that Q1 is actually redundant. It will try to optimize the circuit for you. Okay, if you don't have, in this case, if you don't have this Q1 in the output list, all right, in the output list, all right, you only have Q2 as your output, so you will get one flip-flop only. Okay, so that is wrong actually, because we want this kind of circuit, this type of circuit, right? Means that if we want to design a sequential logic flip-flops or latch, use this non-blocking blocking assignment. Use blocking assignment is dangerous. Dangerous. You can use, but you need to be careful. All right. So to overcome these issues, this problem, we use what we call non-blocking assignment. So instead of using the equal sign, now we use less than and equal. Actually, this is not less than and equal, and in Verilog, this is assignment symbol, but non-blocking assignment. Equal also, equal also. All right, we call it non-blocking assignment. So same code. See, this is the same code. The only thing is you change this to this, then you will get this one, because when you use non-blocking assignment, the Verilog compiler will evaluate the statement inside the always block separately, one by one. All right, it will not in sequence. All right, so D Q1 is D and Q2 is Q1. All right, then you will get this circuit. All right, so for conclusion is that after this, when you want to design the combinational logic, combinational circuit using behavioral modeling, all right, you are recommended to use blocking assignment. Means that this way, all right. When you want to remember, when you want to design combinational logic, means that you don't have clock, you don't have flip-flops, all right, then you use blocking assignment, just like what we did in chapter 1, 2, 3. All right, but later on, when you want to design sequential circuit, you want to design flip-flops, use non-blocking assignment. That is the rule of thumb. All right, I think the rules is here. All right, guideline. Code all sequential logic using non-blocking assignment. All right, use this symbol. But combinational logic, use blocking assignment or this assignment. Then you will be safe. All right, easy, Look at the second example. For example, you could this, and remember, when you have post-age clock, you will get flip-flop for sure. All right. So now you see you have two statement here, and you use blocking assignment here. All right, and F is from this F in this case. So the Verilog compiler will synthesize this code to this circuit. All right, where you see G is F or X3. G is X3 or F, and this is F because F here is actually X1 and X2. X1 and X2. This is F. All right, the Verilog could understand that this is F and this is X3. All right, and we OR and you get G here. And for the F, because this is different, another flip-flops, all right, is X1 and X2. X1 and X2, you have F. All right, but if you use blocking as non-blocking assignment, you will have something like this. All right, where F, yes, X1, X2, you have F, But G is this. All right, F from the first from the second flip flop, or this one. All right, and you OR with X3, and you get G. All right, so see the difference there when you use non-blocking assignment as compared to blocking assignment here. So you need to be careful. You want this circuit or this circuit. If you want this circuit, you need to use this assignment. All right, so need to be careful. Okay, so that is the flip-flops, which is the uh, very important um, or fundamental component that we will use to build what we call a register. All right, because one flip-flop is only one bit, and I remember to design a system, we're not looking at one bit, bit by bit. No, we will look at the data size, means that more than one bit, whether 4 bit, 8 bit, 16 bit, 64 bit, and so on. All right, so what if we want to store a data? All right, so if we use a combinational circuit, we cannot store the data, right? But to store the data, we need to use the sequential circuit. And what kind of sequential circuit that we need to use in order to store the data? All right, means flip-flops, but flip-flop only can only store one bit. All right, so to store more than one bit, we need to use what we call a register. Actually, the register is the flip-flop that are connected together. All right, to form a register. For example, this one is the 4-bit register. Okay, where you can see that you have four flip-flops here connected like this. Then you get the 4-bit register. Okay, so we will see here. This is the input A. So A is 4-bit. A3, A2, A1, A0 is the input to the flip-flops, and the output is Q2, Q3, Q2, Q1, Q0, and connected to the same or common clock here, the same clock signal. Then you get the register. So actually easy, right? Just have more than one register flip-flops, and you can have register already, right? Just connect them to the same clock. All right. But now how to describe this, how to create this using Verilog. So this is how. Okay, so let's, for example, name this circuit as rack 4, register 4-bit, clock A and Q. So you have A and you have Q here. All right. Input is 1-bit clock, but A now is 4-bit. All right, 320, 320, and Q also is 4-bit, 320. All right, and again, Q must be declared as rack because here we will use always block and we assign the value to Q, and this Q must be rack. All right, and you see what is different between this and this. This is it different? One flip-flop and more flip-flop. No different, right? A is assigned to Q. But the difference now is that A is more than one bit. Q also more than one bit. Then you get register. Okay? So the design a register is pretty straightforward, simple. Just like you design a flip-flop. The only different thing is that you you have more bit for A and input and output. All right, or you can design using behavioral not behavioral hierarchical design methodology. All right, where you design the first flip-flop and you connect this way, right? Connect like this, and you can get 4-bit flip-flop also. And this is the symbol block diagram of the uh, circuit, or what we call the functional block diagram. So you can see you have flip-flops, and this is input is 4-bit and output is 4-bit. All right, so this is actually a register. Okay, now we have what we call a parallel load with reset register. All right, now we have load and reset. Right, how to create this? Look complicated, but actually when you see this, yeah, the circuit is actually pretty the same. Right, you can design this using a hierarchical design methodology, or you can do something like this. All right, so let's look at the code here. All right, module red 4, clock, reset, load, A, and Q. So let's look at the input list. So you have clock. Where is the clock? Here is the clock. So this is the same clock, yeah. All right, the same clock. This is connected together. Okay, and you have reset. All right, now you have reset in your flip-flop, in your register, and you have load signal. Load signal. So what is load signal? Load signal is actually a signal that control the input to the flip-flop or to the register. So means that if load signal is not active, the data A here is not enter the register. But if load signal is active, or select the A input, so the data will go to the register. So that is the load signal. And you have input A 4-bit and you have output Q 4-bit. All right. And see, look here, we have post age clock. All right, and now we have reset. Now we have reset, and you need to write post age reset also. You cannot write only reset. Okay, because Verilog only allowed if you use post age or net age. Here must be post age or net age also. All right, in for positive, the keyword is neg and neg edge, neg h. All right, so this is positive h, positive reset. Post h is means that reset is active high also. Positive active. So we have reset signal, and if reset q will equal to 0, means that if we reset is equal to 1 or active, yes, the output q here should be equal to 0, right? When we reset the register or we reset the flip-flops, the output of the flip-flop or register must be 0. And if reset is not active, all right, if reset is not active, means that in this case reset is equal to 0, the output of the flip-flop or the content of the flip-flop here is depend on the load signal. All right, so when load is not active, there is nothing. But if load is active, if load equal to 1, in this case we load data A. A is assigned to Q. We load data to the register Q. All right, A will go to Q, but you don't have else here, right? So what is else statement actually? Else Q should be equal to Q. See, you have multiplexer here. If load equal to 1 here, A will go to Q. A will go to through this line, right? Go to Q. But if load equal to 0, what happened? Q should be equal to Q. You see, Q should be equal to Q. This is the feedback line. All right, but you don't have to write there. The Verilog compiler will give you automatically this line. All right, if we assume that if load equal to 0, Q should be remain Q. Q should remain Q. All right, so you will get this circuit when you write like this. And remember that this reset is asynchronous reset. What is asynchronous reset? Asynchronous reset is that This reset signal is actually not edge triggered, but in Verilog you require to write this. Okay, write this. If you don't write this, it will give you error. Okay, but this reset is actually asynchronous. Asynchronous means that it is level sensitive, not edge sensitive. Means that whenever reset signal is active, go to high in this case, Q will go to 0. All right, go to 0. Okay, so that is the function of this reset. What about synchronous reset? Synchronous clear, do you have that? Yes, you have. If you want to use synchronous reset, no need to write reset in this sensitivity list. All right, just push its clock, close, and you have reset here. Then you will have the synchronous reset. All right, but we will not use synchronous reset in this course. We will use this asynchronous reset. Okay, and this is the symbol. So you have load, you have reset, and you have input and you have output. Okay, this is the another example. So this is a 16-bit register. You see what is inside is the same, still the same with this one. The only difference is this, and this one is quite good. This good because we use parameter n equal to 16. All right, and you see the input here we use n minus 1, which is 15 to 0. All right, means that a is now 16-bit. All right, 15 to 0 because n is 16, and also q is 15 to 0. All right, 16-bit, and this one is still the same. All right, now when you want to use this code to design a bigger or smaller register, you just change what? Change this. Yeah. When you want your register to be an 8-bit register, so just change this to 8. And yes, you will have 8-bit register. When you want to have a bigger register, 32-bit, for example, you change this to 32, then you get the 32-bit register. All right. This is the beautiful of Verilog. Okay, right. And last one for the register, is it the last one? I think the last one. The last one for the register is this one, the shift load register. What is the shift load register? The shift load register is the register that you can load the input parallelly and get the output parallelly, or you can get the output bit by bit, shift from the left to right or from the right to left, depend. So in this case is the shift from the left to the right. So looks complicated, but if we look carefully, this is actually not that complicated, not that difficult. So let's look at this. You have the multiplexer here, and you have this control signal. The name is shift load signal. And when we look at shift here, we have bar there, means that if if this signal is 0, means that we will perform the shift operation. When this signal is 1, means that we will perform the load operation, just like what we did in the subtractor circuit, right? Same thing. And look at this. When this equal to 1, what happened? When this line equal to 1, so we will see that the input to the flip-flops, to the register, is from here, right? From here. This one, from here. Means that here also the same, from here, means that we load data, right, from here to the register whenever load equal to 1. But when this signal, the load shift signal equal to 0, now we see this. the input to the register is from the this line 0 0 0. So from this line, so the input to this register is from here. All right, so it will go here to this, and the input to the second register is the output from the first register, first flip-flops. All right, so but we can see that the data will shift from here to here, and shift from here to here, and shift from here to here, and from here to here, then go to the Q0. All right, so shift and load depend on this signal. Now again, how do we code, write the code for this? Okay, before that, we can have uh, maybe we can write the code for one flip-flop with multiplexer in front. So we can write something like this. All right. So we have marks with the flip-flop D0, D1, select, clock, Q, and this are the input, and we have only Q input. And here, if you write like this, of course, you will have the multiplexer in front of your flip-flops. You will get something like this. Okay, I used this. So when we have this code, so this actually is something like this. You will have flip-flops, and you will have the multiplexer, and this is your D of the flip-flop, and you have Q, and this will be the post edge. All right, and the output here named Q, and you have 0, sorry, 1 0, and if 0, what happened should be this is not select, so you have select cell, and if 0, so Q should be D0, so it should be D0 here and D1 here. If 1, then D1. So if you write the code like this, so you will get this, the flip-flop with multiplexer in front of it, just like this, actually this one. Or you can do something like this. Use the data flow modeling to get this D. So you need to have a wire D. Wire D. This is name D. So D, you use this assignment. Okay, cell depend on cell D1, D0. All right, D1, D0, and you will get this D, and this is multiplexer. All right, and this is the flip-flops here. Okay, so you can have Q, D. All right, so the same circuit actually. Now this is how we create the shift register, load shift register, the this one using hierarchical modeling, and use this one as a sub module. Right, so when you look carefully here, all right, so this one is named stage 3, means that this one, stage 3. Okay, And we see that we have W, R3, L, clock, Q3. So what is R3? R3 is actually, if we look at this, R3 is D0, right? D0. This is R3 here. W, oh no, R3 is, W is D0, eh? W is D0. So this is W, this is R3, and what about this L? This is L, connector L, and this is clock, yes, clock, and this is Q3 in this case. Okay, so this is actually R3, this is R2, this is R1, this is R0, and this is our W. Yeah. So if 0, all right, if 0, so the input is W, yes, D0, W, and R3, if load equal to 1 is R3 and R3, this one, and the load and the Q3. All right, so that is the first flip-flop, the second one, third one, and last one. So you can try to do this, and we also can use one-time code like this. Means that we design the 4-bit register from the start. So we can use this way. Same thing, art L, W, clock, W, and we have input art, same thing, clock, and output now right Q, 4-bit Q, and post H, if L, if load, all right, if load equal to 1, so what happened? So means that the output, the Q is receive the signal from art, or art is assigned to Q, or Q is equal to art, means that the value, the art, will go to the register. All right, and if load equal to 0, in this case, if load equal to 0 means that we get the input from this serial input, or W. So we see this, we use non-blocking assignment, right? Because this is a register sequential circuit. Q1 is assigned to Q0, Q2 assigned to Q1, Q3 assigned to Q2, and W assigned to Q3. All right, just exactly this. All right, Q0 assigned Q1 assigned to Q0, right? Q1 assigned to Q0, Q2 assigned to Q1, Q3 assigned to Q2, and W assigned to Q3. So this will give you same circuit as this one. All right, but this one using the hierarchical code, where you need to have this mux f mux s x mux DFF, mux DFF, which is this one, and you can create this, and this one you don't need that, which because you design the 4-bit register from the start. All right, straightforward. So this is how. And when you want to design a bigger circuit, for example 16-bit, you can use again parameter. All right, this n equal to 16. So here means that art is now equal to 16 bit. All right, 15 to 0, and Q also 16 bit, 15 to 0. And we can use because here, if you want to have 16 bit, so you need to write from 0 to 15, yeah, and that is 16. If we want to design 32 bit, so the you need to have many statements here. All right, so this is a waste of time, right? So you can use the for loop here, right, where we can see that we can use for loop for k equal to 0, k less than 15. All right, k, and then if less than 15 you increase k by 1, and you have this. So the one is in the for loop is this only, this one only. This one is not inside the for loop, because you don't have begin and end, right? So the statement after the for loop is loop. This one is not loop, not inside the loop. Yeah, you need to know that. Just like the C programming, if in C programming, if you have this, then all of these are inside the loop. But if you don't have, only the statement after the for statement is loop, is inside the loop. But this one is not inside the loop. All right, only unless you have begin and end, then these two will be loop, inside loop. All right, but again, this is not depend on k, and we don't have k there. All right, so uh, so if you have 15 bit, right, n equal to 16, so you can have something like this. K start with 0, Q1, and you go back, right, because it's still less than 15. So you increment k, you have Q1, Q2, Q3, Q2, Q3, right, until the condition is met. So here it will automatically generated for you. All right, when you want to change to 32 bit, you just change this to 32 and you can get 32 bit shift register already. All right, if not, you need to write very long like this. Yeah, so this is the good thing about Verilog. That's why we use Verilog in designing the complex circuit. All right, this is actually the same. Yeah, you have multiplexer and you have E can be load signal, some same thing actually. All right, so we will have a break, 10 minutes. This is 10:01, and we come back at 10 minutes. Okay, to start with counter.